Another question that I had for me to review was to go over what the length-tension relationship is, what it does, and how it applies to the course. So before we move into the actual relationship itself, let's kind of break things down from the very beginning and understand if we're talking about force, the first question we need to be answering in that case is what determines the amount of force that a muscle can produce. If we think back to kind of the basic structure and function of muscle, what we know is, of course, the sarcomere is what we determine as the functional unit of skeletal muscle. And so realistically, we call it that because the way it works is it tries to squeeze Z-line together, Z-line to Z-line, and tries to pull the muscle together. When it does, that muscle shortens, and ultimately the more sarcomeres we have pulling together will ultimately generate more force. As we've learned, what determines how much force that sarcomere produces is this statement right here. The number of actin and myosin cross bridges that can occur will ultimately determine the amount of force. So more actin and myosin cross bridges are formed, more force. Less formed, less force. In other words, we can say that cross bridges mean more power strokes. More power strokes means that Z-lines that both of the Z-lines on the outside of the sarcomere become closer and closer to each other, and the closer those Z-lines all are together at the end of a muscle contraction, the more force we ultimately produce. And we have kind of a cheesy cartoon here to kind of demonstrate. Here's a Z-line, here's a Z-line, and here's a Z-line. The pink here are our actin or our thin filaments. And the green here is our myosin or our thick filaments. And again, as we very well know, muscles contract by cross-bridge cycling of a myosin head, grabbing on and pulling Z-line to Z-line, which ultimately leads us to this contracted muscle here, where two side-by-side sarcomeres both pull towards the center, both causing the Z-lines, of course, to come closer, causing the sarcomere to become shorter and muscle force to be produced. So that is ultimately the way we can think about it is during a muscle contraction, the closer we can pull Z-lines of sarcomeres together, the greater the force production as we work through. So to further illustrate this point, what we're going to do is we're actually going to look at the length-tension relationship because it is how we define how the amount of force a muscle can produce is ultimately can be determined by the starting length of that muscle. So I'm going to take three scenarios as we look. So first let's take a look at what I would consider kind of a normal skeletal muscle. Here's a little better drawing. We got our actin, we got our myosin, here's our Z-line, here's our Z-line. Okay. And again, here is the resting or starting length of the muscle. And as you can see, when we generate a muscle contraction, right, myosin starts cross-bridge formation with actin, starts cross-bridge formation with actin, ultimately pulling this shorter. And if we were to actually take a ruler, we would see that these Z-lines are now closer together, meaning force was produced. What happens on the kind of opposite end of the spectrum if we were to have the muscle stretched incredibly far apart? So here's an example of that. If you can look, here our Z-lines are stretched incredibly long, or our starting length is incredibly long in these muscles. If the muscle in this resting or starting length here is given the signal to release calcium and cause a muscle contraction to occur, right, we can envision that this myosin head would try to cross-bridge with an actin, but guess what? It's stretched too far apart, therefore myosin and actin can't interact. If there's no interaction, there's no cross bridges, no power strokes, and no ability to then move the Z-line to closer to each other. And so if we were to take a ruler, we would see that these two Z-lines haven't moved at all because no cross bridge cycles have occurred just based on the length of the muscle being too far apart. I'll note that this is non-physiological. This doesn't happen in any normal healthy muscle, but it's great to kind of demonstrate this principle. On the opposite end of the spectrum, we can take a look at a muscle where the sarcomeres are already compressed and nice and short. So in this scenario, here's our really tight Z-line. We get the signal to contract, but guess what? If we measure the space between Z-line to Z-line, There's no change in the distance between Z-line to Z-line because there's nowhere to go. There's no space to pull actin, right? They're just going to come in here, and we can imagine that they bump up against each other and no movement occurs. So therefore we can say a resting length too long means that we get less force production because we get less actin and myosin cross bridge formation. We get too short of a resting length, and we get where we aren't able to kind of pull Z lines closer together, and therefore we reduce muscle force production in that way. And so ultimately we can have some range in between. And that kind of range, as we go from being way too extended or way too short to extended, ultimately gives us the graph of our length-tension relationship. Here's how that kind of looks out. Again, here's the example we laid out of being way too tight such that we get no cross-bridge formation. We're so tight and compressed that nothing happens. Right? And here's the other end of that spectrum in which we showed where they're so far apart, no cross bridges can actually be formed. Again, as I mentioned, we're talking way out here in this green half. And notice in this green half, this is actually not anywhere in physiology. So if we were to experience this, then the range of muscle, that our muscle would no longer be attached to our bones, in other words. Right? Instead, we spend the part of this in our of actually being attached to the muscle here in this orange area. And what you'll see is a couple things. One, we're still able to generate a pretty decent amount of force as long as our muscles stay attached to the bones. So we never really experience any true major complete loss of function, loss of force based on this length-tension relationship. Instead, we stay in a pretty narrow range. We can say, however, that there is an optimal length. And this optimal length we can be defined as the perfect positioning of these sarcomeres such that actin and myosin give us the greatest number of cross-bridge formations to occur during a muscle contraction. Okay? So that's what we consider to be the optimal length in a skeletal muscle. Okay? One of the really great benefits is you'll notice that for most muscles, and I'll say this is specific to different skeletal muscles, and so we're just kind of speaking in generalities here, but for muscles, there's actually a nice little range. That optimal length is, yes, there's 100% of optimal length. We go a little bit one way, and it's still able to generate the maximum amount of force. We go a little bit on the shorter end, we're able to generate maximum force. However, we can, especially if you think about in very extended period of times, and you can experience this of trying to get a weight started. So if you're trying to do a barbell curl, right, trying to get the weight started is oftentimes the most difficult because our muscles are so stretched. We're out of this optimal length, and we're then unable to produce a maximum amount of force. Again, good thing is optimal length for most of our muscles exist in this range, and this range for the most part is kind of the most range of motion in the muscle. So hopefully this kind of gives you another perspective showing how those cross bridges actually look in a kind of exaggerated shortened length and an exaggerated lengthened length, and how we can realistically kind of settle in on the number of cross bridges that allow optimal formation, which then allows optimal force to be produced.